Hi. So today we are going to study plane curves and the curvature. It's a very important lesson today. Okay. So this is the time we're going to study curvature. Right. So, well, given a curve in the space, right? I want to use a quantity to describe how curve of that curve at that particular point. Okay. And we need to find the expression so we can use it to compute the curvature. And that expression, that's all what you get, should be independent of the choice. Like for a curve, right? You have so many parameterization for the curve. So I think the best way to do it, we fix one parameterization. We assume, this is the gamma, okay? This is the arc length, okay? So we assume that it has a unit speed. So that means the derivative is always, the length is always given 1. So under this assumption, that's unique, right? Otherwise, we can find the expression using different parameterization for the curve C, okay? And the parameterization was arc length, right? So it's unique, almost unique. Okay, so that's why this is what we want to begin with. Then we use that to define the curvature. Okay, the definition is very simple. Okay. All right. So here's how do we do? We differentiate because this is norm, right? So prime, the dot product, and it could be also inner product, doesn't matter. It's going to be 1, right? Then I differentiate on both sides by the product rule, right? That's going to be 0, right? And the product rule tells you it's twice of a double prime, and that's going to be 0, okay? So what does that tell you? That tells you gamma double prime is going to be perpendicular to this. And based on the observations of many curves, we find out the length of the second derivative really tells you how curved of the curve in that space. Okay? So based on our observation, like if we have something like this and something like that, okay? And it looks, clearly the curve on the left-hand side is more curved than the curve on the right-hand side. So we find out this is longer and this is shorter, the second derivative. Okay. So it is natural to define the length of the second derivative, okay? And we call it the curvature of the curve at that particular point. And Ks is called the curvature of this curve C, okay? At that particular point. All right. All right. Now, let's take a look example. And we want to know indeed that this quantity indeed is a good quantity, tells you the truth of how curved the curve, right? So the example we want to take a look at is a circle with a radius r. Okay, the reason S divided by R is because this is going to be the unit speed. This has a unit speed. So it's going to be negative sign SR and cosine SR. So the length is going to be what? All right, so length is going to be what? Okay, the length is going to be 1, and then we can differentiate twice, and I'm going to get negative 1 over cosine RS, and then negative 1 over sine RS, right? Right. So the length, how does it look like? It's negative 1 over R, right? Cosine RS and the sine SR. Okay. So let's look at the picture. Okay. Let's look at the picture. This is a circle. Okay. This is a circle. And the radius is R, right? Then I find out the so-called curvature is the length of the second derivative is going to be just 1 over R. Okay? It is pointed to that direction. And the length is going to be 1 over R. So, and this is curvature is going to be 1 over R, right? So when the circle is getting larger, okay? And yeah, for example, this is R prime, right? Then this is a curvature here is going to be 1 over R prime, which is much smaller number. So that's reasonable, okay? Because it's getting, when the circle is getting larger, the curve is more flat. The curvature is almost equal to 0, okay? Right? So I think this is a right definition. So you can introduce some new quantity to describe the geometric properties of some curves. But then two things you have to answer. Well, two things you have to do. Okay, one is have to make sure your expression is well defined. You know, it's independent of the choice of a particular parameterization. If you use arbitrary parameterization, but if you use a special parameterization, you don't need to worry about that because that's, you know, the parameterization, you know, was a unit speed. Okay. Second is you have to use a special example to check. Does it make sense? You call it curvature, right? And you get that it's constant. Yes, you know, the circle should be curved evenly around here, right? And this should be the constant curvature. Number two, use your formula, you calculate, right? And the curvature should be getting, it should be less and less if the circle is getting larger, and that also matches. Okay, so this is right. It's the right definition. Okay, so now you have a right definition of curvature. But in reality is the curve is given. What I should say, it's not always given by parameterization with arc length. Okay, in that case, what they can do, right? How to compute the curvature? How to compute the curvature? A curvature at point P on the curve C if it is parameterized by gamma T. It's not necessarily, T is not necessary to be arc length. Okay, just an arbitrary parameterization. Okay, so how do I do that? Right? Yeah. So you have to solve this problem. Okay, so this is a curve, and I have a gamma T here, and this is a curve in the alpha, beta, you know, right? And this is T, and here's here. Okay. And it's if you have to find a new parameterization, then it's almost impossible, because if S is, for example, let's try an arbitrary point here, and this is a, this is a point, yeah. If it's going to be, okay, so T and a T naught, right? Okay, this is arc length, and if you're able to solve it, evaluate, and then you can yeah, if you can get S of T, then you have to solve for, right, find the inverse, right? And this is, I use well, I should use another notation, phi T. Then you solve for this, then you have a gamma. You can define the new one, which is going to be gamma phi, right? And then you get a new parameterization. Then you find the derivative. Okay, second derivative, then you compute curvature. But each step, it's challenging. First of all, how to evaluate this integral. Okay, if the interval cannot be evaluated, and you cannot get an elemental function to describe, and how can you find the t, right? Solve for t, okay? And this is not it's not easy. Okay, it's gamma tilde s, okay, right? And they match. So what I'm going to do is, assuming I already find it. Okay, let's say assuming I already find out. Okay, so okay, I differentiate. Then I get, I'm going to use this dot, use this notation. Okay, then I differentiate this. Okay, it's bad, right? So we don't know this yet. Okay, it's a derivative of the inverse function. Right, then this gives me my curvature. So I differentiate as a product or in a channel, right? So double, and then I have a ds. That's a square, and then all right. So I just want to find the length of that. What I'm going to do is I look at the product, dot product. Okay. Okay. So if you look at dot product, this times that is going to be 0. So you only get gamma dot. Okay, and this will be ds cube, right? All right. All right. Now it turns out this is a in 3-dimensional space. Okay, we can do that. It's a 3-dimensional space. Okay, at the very beginning, yeah, in 3-dimensional space, we assume that you can talk about the cross product. Otherwise, you cannot. Right, in 3-dimensional space. Right. Then on this left-hand side, you take a look at this is a gamma prime s, and this will be gamma double prime s. Right. The dot product, right? The cross product gives you another vector. It's perpendicular to both of them. Okay, and the length is, it depends, right? So the length is actually is going to be this length. Okay, it's really just equal to the length of the vector, right? And that is going to be ks. Okay, the curvature. Right. So on the other hand, yeah, if a gamma 2 the double prime is unit vector, then the cross product gives you another unit vector, so the length will be 1. Otherwise, yeah, this is It's the same. Now, on the other hand, right? On the other hand, you have okay, and this is a derivative of s and the q. Okay, so now I'm going to change this. Okay, we know that t equals this, right? T equals this. So there's a famous formula in the calculus, right? Calculus 2. Okay, so the derivative dt ds is going to be, okay, right? It's going to be, actually, it's going to be t prime. And, right? So it's going to be prime t, okay? Right? And phi prime t, I know that phi prime t from the very beginning, phi prime t is going to be just, okay, just equal that, okay? So this is a, yeah, this is a dTds, right? So now it's going to the denominator. So ks is going to be and here. So we find a nice formula, okay? The relationship between s and t is already given, right? So this is for an arbitrary parameterization. This is how do we use it on the computer curvature, okay? So let's take a look at an example. Okay, here's a good example. Here's an example. Gamma t is going to be a cosine t, b sine t, and I'm going to use a here, and the b and the t. Okay. Okay. So I don't know whether this has a constant speed or not, right? Let's differentiate. And that is going to be negative a sine t and a cosine t and the b. Well, it's not too bad. Okay, so that's going to be square root of a squared plus b squared. All right, so you have two options. One is in order to find the curvature, right? One is a reparameterize, yeah, to get arc length, right? Or use above formula. I'm going to use above formula to make it easier. So I'm going to look at the second derivative, which is going to be negative a cosine t, negative b, negative a sine t, and 0. Okay. Now I have to do the cross product, right? I hope you remember how to do the cross product. Right. It's I, j, k, and the negative a sine t, a cosine t, and the b, and negative a cosine t, negative a sine t, and 0. Okay, let's do the computation. And this part, I will get ab sine t, I negative. In this part, I think it's going to be negative ab cosine tj. And a square, yeah, then that's just a square. Okay. Yeah. Okay. So the length of this vector is going to be, I think, just the square root of AB squared plus A squared squared. And well, A squared, I can take A squared out, right? I can take A squared out. What's inside is A squared plus B squared. Yeah, A squared, when you take it out, you can stay. Right. So finally, the curvature is going to be right, it's going to be A squared plus B squared, and that is we also have, we already defined the length, right? We have defined the length, A squared plus B squared, A squared plus B squared, and square root and cube. Okay. Right. Right. Then finally, after you simplify it, yeah, you will get we assume here A, B are positive, right? So then you get A squared plus B squared. It's a constant. So constant curvature. Constant curvature. How does the curve look like? Okay. This probably is just a curve. Yeah, spray around that. And this is it's constant curvature. It's constant. Okay. Yeah. And this is a good example. And then let's look at another example. I'm very curious about the parabola, for example, right? This one has a constant speed, So even you can use a parametrization arc length to find the curvature. So second example, compute the curvature on the plane y equals x squared. The parabola. So this is a parabola. I think the curvature here at the vertex is a maximum, and gradually the curvature is going to be smaller and smaller, and in infinity, if you look at the parabola, the curvature is almost zero. Okay, so that's why it's almost a straight line. Right, to compute curvature, I have to find parameterization. I really don't need to find the special parameter arc length. Parameterization with unit speed, it's very difficult to do that. So what I'm going to do is I just find the parameterization t and the t squared, right? This is good enough, okay? Yeah, when we talk about dot product, we usually see in three-dimensional space, okay? If you wanted that, so this is a three-dimensional space. I put a 0 here, okay? Okay, so the gamma t is going to be 1, 2, t, 0, and the gamma double prime t is 0, 2, 0, okay? So the cross product, it's going to be ijk 1, 2, t, 0, 0, 2, 0, right? Let's compute. So it's going to be 0 I, that's right, and minus 0 j. Okay, the last one is 2. Okay, yeah, just 1 times 2 minus. Okay, it's not too bad, right? So the curvature at gamma t is going to be the length of the cross product divided by this. So it is going to be square root of 2. Then the length of that is going to be 1 plus 2t squared, right? Square root 2t squared, the length. So you get a curvature like that, okay? T is not the arc length, I have to say that. That's okay, right? So it tells you, this is a curvature, right? And clearly, the curvature when t equals 0, at the t equals 0, that's going to be square root 2. Right? So curvature, the vertex, the curvature of the parabola, the vertex is square root 2. Right? If my computation is correct here. And we also know that as t approaches positive infinity, negative infinity, the curvature approaches 0. Okay, so nearby infinity, almost no curvature. It's a straight line, the parabola. Okay, we did not know that before, right? Until we study geometry. I can tell you the curvature is almost 0. Now, why curvature is 0? It must be a straight line. That's a different story. So we can look at in the next section. Okay, so curvature is almost 0 means the curve is almost a straight line. Okay? Not straight line. It's I should say later on we're going to study curvature and the torsion. Yeah, I shouldn't say that, but it's a more flat. Okay, I should have said that. Okay, it's not necessarily straight line in three-dimensional space. Right. Now I'm going to consider plane curves only. Okay. So yeah. Yeah, plane curves. Then you can look at the curves in three-dimensional space. Plane curves. Plane curves. Well, it's in the plane. X-axis or Y-axis. We have a curve here. Plane curve. So I can assume that gamma prime s is going to be the length is going to 1. Okay, I assume that. So now the curve can be you can let me draw a picture slightly different. Not always curved in one direction. It's probably like that. Right? So gamma s, the second derivative. Okay, let me mark it. How does it look like? In here, it looks like that. Okay. And here it's curving in that direction. Okay. Yeah, this is a second derivative. Okay. It's not always in one direction, the second derivative. And here it's probably gamma prime is going to be 0. Okay, so I'm going to fix. Yeah, this is a tangent event. Okay, gamma prime is. So I'm going to use a right hand to denote the normal vector. Okay, so I introduce let ns be the unit vector perpendicular to gamma prime s. Okay. Then the notation is counterclockwise. If this is gamma prime s, This will be ns. Okay, how do I say? It's defined this way. That's the only unique one. Okay, rotate counterclockwise the unit vector. You will get this so-called normal vector. But on the other hand, right, this is a perpendicular to that, right? Right. Okay. So you can express it in the form right? Right? It's proportional, but it's possible the second derivative in other direction. In this case, the curvature will be a negative. Okay, this is called the sine curvature. Okay. Now, the relationship between the sine curvature and the curvature will be it's a absolute value of this, right? Second derivative is going to be right. It's going to be absolute of the normal curvature, the sine curvature, and then and it has a unit length. That's why it's gone. Right. So this is the curvature. Right. So the relationship between curvature and the sine curvature is just this one. Okay. But the sine curvature could be negative, but the negative curvature can be always positive or zero. All right. So this is what we have. All right. Now what? I'm trying to show you how to determine the curvature by the sine curvature, determine the curve by the sine curvature. Okay. So go back to the picture. This is a gamma prong, yes. Okay. And this is a ns. Okay. This might be gamma double prime s. Okay. Right. And our picture here is gamma double prime s is going to be ks and ns. Okay. So I'm going to let this one as xs, ys. So that means x of square ys square is going to be 1, right? It's a unit vector. All right, once you're given the two components of this tangent vector, then ns can be written in the negative ys and xs. Okay, believe it or not, right? Because when you have a vector here with components a and b, and then the one perpendicular to that will be negative b and a. Okay, this is the right angle. Okay. So this equation implies the following. Okay, the double derivative. Okay, it's going to be this, and the ks, negative ys, and xs. And then you have x prime s equals negative ks, ys, y prime s equals ks, xs. So you get the system of equations, differential equations. can we solve it? Can we solve it? Yeah, think about it, okay? Can we solve it? All right, so I think we have a solution. So here's a solution, very simple. It's going to be cosine of the integral of ks tau d tau, and this can be starting from 0 to s, okay? And the plus value, okay? This is a initial value, okay? ys equals sine right. And so this will be cosine phi, yeah? Okay, when s equal to. And in ODE now, you can say, well, why do you know this? Well, you just double check it. You know, solution is unique. Okay, solution is unique. So first of all, satisfy this initial condition. All you have to do is just verify, differentiate, and you find out this is indeed a solution. Okay. Right. So you can check that when you verify that. Okay. Right. X prime s is going to be okay. This is the cosine become negative sign. Right. Blah blah blah. Right. And times the derivative inside is just ks. Okay, this part is y. Okay, so it's negative ks and ys. Yes. Okay. So similarly, y prime s equals cosine of this, right? And ks. And this is nothing but x. Okay, so ks. Right, indeed, there are solutions. All right, so the solutions, and okay. So this phi is the angle. Okay, let's take a picture. Okay, at this point, we have gamma prime, right? This is written in the form. So we can assume that this is a phi, okay? Okay, right? All right, now I'm going to introduce let phi s to be this will be the angle we call the turning angle of gamma, okay? So it is called the turning angle of gamma, okay? All right, and it's interesting, right? And y, this is an angle. So think about that, right? X s is going to be cosine ps. Ys equals, yeah. Am I? Yeah. Sorry, I shouldn't use it. Yeah. So this is a sine dx, right? And gamma prime s is going to be, remember, it's going to be xs, ys. Okay. So it is reasonable to think about at an arbitrary point here. This is a gamma prime s, and this should be the phi. Okay. Right. But that phi can, it maybe have a large value, but it's a smooth function, right? It's differentiable, right? It's differentiable. Right. So the derivative of the angle is going to be the curvature. So this is another geometric meaning of the curvature. The curvature tells you how fast the rate of change of the angle, this particular angle. Yeah. Yeah, let's take a look at, this is a useful formula to actually calculate the curvature, okay? So here's the example. I like the example. So gamma t equals t hyperbolic cosine t. Okay. Can we compute the curvature? We compute the curvature in two different ways. One is using formula, right? You view it as a curve in a three-dimensional space, you can use a cross product. Okay. Compute the curvature. Let's compute the curvature. So I'm going to modify this, view this as a curve in three-dimensional space. Then you can talk about the cross product, right? So gamma prime equals 1, hyperbolic sine t 0, gamma double prime is going to be 0, hyperbolic cosine t and 0. Okay, the cross product. Okay, you put I, J, K here on the top, so you can do quickly. This is going to be 0. This is also going to be 0. And that will be hyperbolic cosine t. Right. So the curvature the curvature at gamma t, okay, is going to be give me this, right? So let's compute it, right? So one on the top is just hyperbolic cosine t. The one in the bottom, gamma prime t is 1, right? 1 plus hyperbolic sine square t and the cube. Right? How can I 1 plus hyperbolic sine square t is going to be cosine, hyperbolic cosine t, right? So this is going to be hyperbolic cosine t, then cube. Yeah. So this is answer. All right. All right, so this is answer. So that means this curvature. Okay, what is this curve, right? Let's look at the curve. The curve is when t equals 0. This is going to be right. I think this is a curve, right? Yeah, gamma t equals t. It's not parabola. This actually is a graph of y equals hyperbolic cosine x. Okay. So at every point, you can describe it in a slightly different way, right? At every point, the curvature is going to be 1 over y squared, right? So when the y is getting larger, okay, then the slope is getting small. The curvature is getting small. I can also measure it, describe it in this form. Here's, let's call it S. So there are many ways to express the curvature, right? In terms of t, express it in terms of t, or express it in terms of the coordinates of that point. Or can use in terms of arc length. Okay, so we let S to be integral from 0 to t 1 plus don't put that in direction. All right, so let's do it. Okay, right, because we already find the derivative. Okay, okay. Then you simplify this hyperbolic sine t dt. So the this is the antiderivative of hyperbolic. Yeah, this hyperbolic cosine t, the hyperbolic sine t. Yeah, so S is just hyperbolic sine t. Now let's go back. So curvature is going to be 1 over hyperbolic cosine t squared. And this is also going to be 1 plus hyperbolic sine squared t. And that's just going to be 1 plus 1 over squared. So this is another way to describe the curvature. Okay. Is there any other way to compute the curvature or express the curvature in a different way? Right? I probably can find the curvature inside differently. Yeah, okay, that's enough. Yeah, we already calculated curvature. So I'm going to look at closed curves. Closed curve R2. So suppose you have closed the curve by smooth, right? Yeah, this is also a closed curve, right? So my theorem, I want to prove one thing. The total curvature, right, of a closed curve, the total sine curvature, okay, which is going to be from 0 to L and Ks S ds. Okay. So this must be equal to 2k pi. Wow. So that's a total sine curvature is going to 2k pi. Now why is this true? Right? I give a proof. Okay. Okay. So I've taken so this is a closed curve, okay? So this is from 0, here's L. L is the length. Okay, gamma S. And this gamma prime S is going to be 1, right? L is going to be the length of the closed curve. So you have a map, right? All right. So R prime X is going to be SYS, right? So we have a formula. We have a formula here, cosine CS, sine CS, okay? What is CS? So this is the angle. Okay, this is the angle. Okay. Where CS is an integral from arbitrary point, it's in L, okay, to S. Here's how d top plus this number. Okay, now what? But we know that gamma prime 0 equals gamma prime L, right? Because it's close, right? We use this condition. So that implies cosine phi L sine phi L is going to be equal to cosine 0 and sine 0. Phi 0, okay, phi 0. Okay. So this guarantee from a trigonometric geometry, this guarantee 3L equals minus P0 equals 2K pi, okay? This is where I took the pi from. And by the above identity, okay, by the above identity, this difference is going to be just from 0 to L, Ks r d. Therefore, we get the following. This implies let me rewrite it clear. So this is always an integer, surprise, right? So in other words, 1 over 2 pi, this from 0 to L, Ks pi s is always going to be a k, integer. And there's a geometric meaning of this curvature here. Okay, k here. K could be 1, could be 0, and it could be, it's called the index of the, we are going to call the index of the closed curve. Okay? So K is called the index of a closed curve. Okay, so let's take a look at what we have here. So example, circle is the simplest of closed curve, right? And or ellipsis, those are simple curves, closed curve. In those cases, k is always equal to 1. Okay. And how about the 0? Let's cancel. How about this one? This is going that way, that way, that way, this way. In this case, I'm pretty sure k is going to be, yeah, going this way. In this case, the curvature k, the total curvature divided by 2 pi. I think this time it's cancelled out. So k is going to be 0 in this case. Yeah. What I want to say here as last is the curvature can uniquely determine, almost unique, up to a transformation. Almost, actually, almost uniquely determined by the curvature. Okay, so let's see. Let's get a formula, right? So here's our question. Okay, still given a function ks, okay, a point and a direction. And a direction. Let's call it x, y, y. Okay, here's a point, P and a Q, a direction. Okay. There is a unique curve. Okay. Gamma t such that right. So in that direction, there's a unique curve going out. It's not necessarily depends on where the function is defined. If the function defined on the interval in a, so this is it's S naught. Okay. So here's the function. We assume the function defined from that. So from beta to or from alpha to beta. Okay. So why this is true? Okay. Curvature uniquely determines the curve, but depends on the the initial position, initial direction. Well, the proof is very simple. Okay, the proof is very simple. Okay, gamma prime s equals xs ys, right? Okay. Yeah, this is going to be a prime s. I shouldn't use x, y, yeah, it's a little bit confusing. But that's okay, notations. I didn't carefully choose a notation. So this is yeah, let's see. What is a bad notation? Yeah, I'm going to I'm going to change. Yeah, it's better to change it right now. It's too late. Yeah. Okay, at the point, X naught, Y naught in the direction A and B. How about like that, right? Okay. Then this will be X naught, Y naught, and here's A and B. So you have this, right? And we know already X prime T is going to be cosine phi of S. Y prime YS is going to be sine phi of S. Okay, and this phi of S is going from S out to S and K S tau d tau plus this. You see? So uniquely, then once you get that, then XS is going to integral for cosine. Okay, and plus this. Okay, let's use you can use some labels, okay? And the YS is going to be. So you can uniquely express the components, okay, in terms of the curvature. Okay? Although there are two integrals involved, but that's what, right? So you can uniquely determine. You can uniquely determine the curve. Okay. So the direction, you see, this is A and B, right? So cosine phi 0 equals A. This theta is sine phi 0 equals B. So once the direction is given, then you determine those two angles, and then you get, the specific solution. So this is you get ideas of how it's uniquely determined, okay? And that's so uniquely determined by the curvature. So today we introduced the curvature, we studied the curvature, the linear curvature, and also tell you for the plane curves, the curvature can uniquely determine the curve, okay? And I give you the formula here. The uniquely determined curve and up to the position and the direction, okay?